Welcome again during our conference. This time we'll be heading to our last part of the conference, focused mainly on methods and techniques that can be used for explaining machine learning models. And we have three speeches. One will be delivered by me. It will be focused on the techniques that we use for explaining CRMs and machine learning in CRM or in tabular data. Then we'll have a speech on explaining machine vision, and finally on large language models. And to move forward, I'm Łukasz Borowiecki, I'm the CEO of Tensenses, and I'm involved in working on working groups on AI in our Polish government, and also in Data Management Association here in Poland. And when thinking about CRMs, we often use machine learning for CRMs. There are many reasons why we use it. So when there are companies who have many clients, let's think of, say, hundreds of thousands of clients, like for a financial institution or in a telco, they use machine learning to predict some behaviors of their clients. For example, they do lead scoring to assess whether a client is potentially interested in buying or if it's a valuable customer for them. They may use machine learning to do proper customer segmentation, or they may be using machine learning to do churn prediction, so to assess whether a client will leave the company and take the services from, for example, a competitor. But the techniques I'll be talking about are not only for CRM, because very similar use cases are in the area of user or patient data, where we want to predict some behaviors or, for example, the effect of therapies. In price estimation, where we use machine learning to predict price, or if we have stock data or time series, we may predict, say, some movement of the market. And the thing is that we use machine learning, and the explainability is a challenge, because machine learning models are inherently complex and opaque. They have many moving parts. There may be some XGBoost, some random forest, some ensemble techniques. They have many elements, and that's what makes it so complex that we cannot easily understand what's going on. So we get a prediction, which may be very accurate, but basically that's it. So we call them black box because we see what we put into the model and we see the output, but we don't know what's going on inside. And if we think of such statistical techniques, of what they do is, first, they make a representation of the world, so they get an understanding. Two, they estimate some parameters, and ideally, if they could also estimate the error of this prediction, it would be great. And historically, we have used regression models, which would represent, say, income of a person, taking into account his age, his education, years of experience. So a few information, and it represents this world and gives us a prediction with just a few parameters. So the good thing about regression is that it gives us this representation of the world. It gives us estimation of parameters and error. However, we cannot truly represent the world, which is complex, by just a few parameters. That's why we use machine learning, which gives us a way better representation of the world, and that's why machine learning is so much better than these traditional regression models. The problem with machine learning is that we don't have estimation of parameters, we don't have the estimation of the error, so we don't get this explainability. And that's the issue, and that's why explainability for machine learning is important, to get these things. So there are two approaches to explainability. One is global methods, which explain the model as a whole. And there are also local methods which say focus on a tiny group, and for this tiny subset, a very simple, say, linear model may be sufficient to give a good explanation. And we would argue that global methods such as Shapley values are simply more useful. So for local methods, they are useful where, for example, we look at a particular thing. We want to get some insight into how the model operates. But when we think of systematic reporting of how a model behaves, we need to look at techniques such as Shapley values. And how do Shapley values work? So this is an example from one of the Kaggle competitions. The goal was to predict whether a person experienced 90 days past due delinquency. So whether the person did not repay a rate on time. And we see that for this particular person, the model says that 9.39% of probability that the person won't repay on time. And the person, its age is 57. He has over 9,000 of monthly income. He doesn't have family members who depend on him for their income. And we have information on his credit history. And with Shapley values, what we can get is something like this. So basically, this 9.39% consists of prior probability of 3% plus specific input of each variable. And we see that the risk comes mostly from revolving utilization of unsecured lines and open loans and of credit. On the flip side, we see that his age helps, his income also reduces slightly his risk, and his credit history also help. So we see that with Shapley values, we were able to decompose this 9.39% into a separate input of each variable. And how do we compute this? So basically, if we had this over 9% for this person, then we slightly change the data. For example, we make him a bit older, and we ask the model, what if he was a bit older, what would be the output? If his income was lower, what would be the output? If there were dependent family members, what would be the output? So we bombard the model with permutations of the data just to force the model to tell us what's the impact of each variable. Literally, that's how it works. And with this approach, we can, to some extent, fix the problem of estimation of parameters. So we can get a kind of regression. So we have machine learning model which makes the representation of the world. We don't have parameters, but we do estimate these with Shapley values. Estimation of error is another topic which is beyond the scope of this presentation, but it can also be computed, approximated. And this comparison with regression is important because if we think about a regression, say we model income based on demographics of the person. First, we add two variables, we get some result. Then we add another variable which makes the model even better. Finally, we add that additional two variables, goodness of fit improves. There were even some changes in the parameters. We think, yeah, great, it's good. We found some interactions, and we are happy, which we shouldn't be, because what happens underneath is that we get multicollinearity. So it means that because in social sciences and in social data, everything is correlated. Like income is correlated with education. Education can unfortunately still be correlated with, say, gender. So things are interrelated, and when regression forces to separate the input of each variable, the estimation of parameters get distorted, and that's why we cannot add many variables, which is also a problem, because if we don't add the variables which should be there, we get so-called confounding variables. So they are not decoded, they should be, and for this reason, the estimation of parameters which are in the model is skewed. And eventually, what happens is that with regression, we get a limited number of variables which we can analyze. And each time we change something in the model, we get slightly different estimates. So the model, like the parameters float a bit each time we change the model, which is also problematic. And with Shapley values, we can, to some extent, fix this. So first we train a machine learning model, which is very good at capturing all those nonlinear relations. It's good at capturing interaction between variables. So model gets a good representation of the world. And afterwards, in step 2, we use Shapley values to estimate the parameters and impact of each variable. And this is beneficial in many ways. So first of all, it captures interactions between variables in a way better way. So the collinearity gets reduced. Because the collinearity is reduced, we can add much more variables. So, and if we add them, we fix to some extent the problem of confounding. The estimation is done only once. So we get rid of the problem that each time we change something in a regression model, the parameters move. Now, with Shapley values, we estimate them once, so they're fixed. And finally, the estimation is done on the level of each person. So it fixes a specific problem of regression that, for example, the impact of, say, education will be the same, say, impact of having a university degree will be the same for everyone in the data, which is not true because it will depend on where you live, how old you are, and, for example, how much work experience you have. So with Shapley values, each time for each person, all the other demographics will be taken into account. So we have specific impact of education for this particular person. So we get a much better representation of the world and much better extraction of this information from the model. And what are some applications? So thinking about machine learning in CRM, what we can do is we can ask questions like that. Does the algorithm treat this person that we had in our example? Does it treat him differently than, for example, other people in this age group? So we can see what are specific things in his demographic that, according to the algorithm, make him different. Second thing, we can quantify the impact of each such demographic. So we get, it's not only that we see it, we have numbers. So with numbers, we can make some calculation. So for example, we can make calculations between age groups. Say we can compare how the algorithm sees people who are 30 years old versus those who are 50 years old. And we can see that some impact of some variables may be very different for these two age groups. It's something which we cannot, it's hard to do with regression. With Shapley values, we have this by design. Also, with CRM, we can use Shapley values, for example, for direct marketing, because we can add variable like if the person received a campaign, and we can estimate the net effect of the campaign. So not only whether what was the how much the people did the person say take the offer or did the person click, we can estimate what was the input of just the campaign into his action. And this is great because this allows us to estimate net effects for separate people or for specific groups. And it's great because we can get an ROI on our direct marketing campaigns so that we know whether the cash was spent well. And if we want to plan further campaigns, we see what worked well and what did not. And also, and just to conclude, it's not only about CRM, because like the example that I was just showing you is about customer data, about clients, but the same techniques will be useful in compliance with the regulators. So, For example, once AI Act is in, and afterwards AI Liability Directive is in, what may happen is that at some point, an NGO will sue a company saying that, for example, my clients are women with children, and they never get discounts because they're women, because they have children. And what you do is you discriminate financially this group, because we know that everyone gets discount, only they don't. So you force them to pay financially just because they are women, just because they have children. And the institution says, well, it's not that. It's because they have different demographics. It's because they have different history of using our services. It's this what the model takes into account. After AI liability directive is in, what the court will be able to do is force the company to explain why the model did this decision. So you will have to show explainability to the court. And with this type of techniques, you can show, you can give numbers and say like, what was the actual impact of each variable? So you can answer these questions to the court. But it's not only that. It's think about fraud detection. So say we have an automated algorithm which flags some fraudulent behaviors. It's great that we have them identified, but maybe you want to know like which specific things were taken into account. And with these type of techniques, we can estimate these too. And finally, asset pricing and management. So think about machine learning, which is used to, say, estimate a price. Let's think about, say, price of a house. So with Shapley values, we can extract information out of such a machine learning model, and, for example, compute what was the impact of number of rooms or the size of the house, and each time it will be the impact of size of number of rooms and size of the house will be very specific to this particular location, because size of the house will have different impact if it's the city center, if it's suburbs, if it's somewhere in the village. So with Shapley values, we can extract the impact of these features, which are very specific to this particular location which we analyze. And that would be it. Let me just check if there are some questions regarding. If you have any question regarding this Shapley values approach and CRMs, please do type this into the chat. So as of now, I see none, but just let me conclude that Shapley values are seen as the best currently way to explain the machine learning used for tabular data. So exactly for this type of cases that I showed you. And they're very promising. It's not only that we can explain the black box models using these techniques, but these particular features which are similar to regression make it also a powerful tool with which we can better understand clients, better understand, say, patient data, and other cases where we have a large volume of data. Are you only seeing demand for machine learning solutions in the current market? For me, it's hard to I don't really understand the question. What we currently see is large demand for language models. However, these use cases for classic machine learning, there are still here and there will be more of them. So, and especially given upcoming regulations, there will be even more work to do around machine learning for CRM and for standard tabular data. Okay, so since we don't have any more questions, let me move forward with the second presentation that we have.